Module 1, Lecture C, Logic and Flow. By the end of this lecture, you will be able to write conditional statements that encode chemical engineering decision rules, use loops to repeat calculations across ranges of operating conditions, and debug simple control flow errors in engineering scripts. Conditional safety logic. If statements. An if statement lets a Python program make decisions by checking whether a condition is true before taking action. In chemical engineering, this can support safety decisions, such as responding when temperature or pressure exceeds safe limits. In this way, the program acts like a decision rule, only triggering the needed action when the current state requires attention. In engineering, an if statement is useful only when its condition matches the real situation being evaluated. It turns measurements into decisions, such as whether a system is safe or needs attention. Correct syntax is not enough. The threshold must also make engineering sense. A wrong limit can lead to the wrong decision, even when the code runs correctly. Safety logic depends on precise if statements because they express assumptions about risk and operating limits. Clear conditions make the reason for an action easier to understand and help programs respond to changes, detect problems, and support reliable analysis. These rules should not replace full safety systems, but they can encode simple decisions when they are based on sound engineering judgment. Python code. If statements. This script shows basic reactor safety logic by checking a single engineering condition. The result changes only when that condition requires it. The reactor's current temperature is 92 degrees Celsius. This real-time reading is used to monitor the system and help ensure it remains within safe operating limits. The reactor's maximum safe temperature is set to 85 degrees Celsius. This limit provides a safety threshold, so the system can compare the current temperature against it and decide whether protective action is needed. The code monitors the reactor temperature and responds only if it rises above the safe limit. When that happens, it increases cooling and alerts the operator to help maintain safe operation. The code displays the reactor's current temperature and its safety limit, both in degrees Celsius. This lets the learner compare the operating condition with the safety threshold and understand whether further action may be needed. The code displays the result of the if statement by printing the chosen decision. It tells the user what action to take based on the reactor temperature, such as increasing cooling and alerting the operator when the temperature is above the safe limit. This script demonstrates reactor safety logic by checking whether the current temperature is above a safe limit. Since the reactor is at 92 degrees Celsius and the limit is 85 degrees, it triggers increased cooling and alerts the operator. The output reports the temperature, limit, and action taken, showing conditional logic in a safety-critical setting. Conditional checks. Conditional checks are decision points in a program that test whether a condition is true or false. In chemical engineering, they represent questions such as whether temperature or pressure is within safe limits. These logical tests turn engineering judgment into actions, helping systems detect when critical boundaries are crossed and a response is needed. Conditional checks should reflect real engineering rules, not just programming logic. Similar tests, such as whether a heat exchanger outlet temperature is above a target or above a safety limit, can lead to very different actions. Engineers must choose comparisons carefully, consider units and data reliability, and understand the consequences. In this way, each condition becomes a formal expression of process knowledge. Safety logic uses clear, conservative conditional checks to protect people, equipment, and the environment. Rather than relying only on simple limits, good rules also consider patterns such as rapid pressure or temperature increases, weak cooling, or sustained unsafe conditions. By encoding these judgments directly, safety systems respond consistently and reflect sound engineering practice without depending on informal interpretation or delayed human action. Python code, conditional checks. Conditional checks help a program make safe process decisions. In this example, the program compares temperature and pressure, then chooses a branch that prints one clear action. The reactor's current operating readings are set to 92 degrees Celsius, 240 kilopascals, and a cooling flow rate of 18 liters per minute. These real-time values provide the basis for assessing the reactor's safety conditions. The operating procedure sets key safety limits for the reactor. Temperature must not exceed 90 degrees Celsius. Pressure must stay below 250 kilopascals, and cooling flow must remain at least 20 liters per minute. These limits define when action is needed to keep the reactor operating safely. The system first sets a safe baseline. Continue normal operation because all monitored values are acceptable. This means temperature, pressure, and cooling flow are within their defined safety limits before any conditional checks are applied. The system checks whether the reactor is too hot, while cooling flow is too low. If both conditions occur together, it treats the situation as critical and starts a controlled shutdown to prevent damage or hazards. The stated reason is the dangerous combination of high temperature and insufficient cooling. This section checks whether pressure has reached or exceeded the maximum allowable limit. If it has, a high pressure alarm is triggered so operators know the system has reached its safe threshold and requires attention. The code checks whether the temperature is above the safe maximum. If it is, it responds by reducing the heat input to bring the system back toward a safer range. The output summarizes a conditional safety check by reporting the system's key status values, temperature, pressure, and cooling flow rate. It then states the recommended action and the reason for it, giving operators a concise view of current conditions and any needed response. This script checks reactor safety by comparing temperature, pressure, and cooling flow with set limits. It starts by assuming normal operation, then recommends action as conditions become unsafe, such as a controlled shutdown when high temperature combines with low cooling flow, a pressure alarm at the pressure limit, or reduced heat input when only temperature is high. It reports the current readings along with the recommended action and reason, giving operators a concise status update. Safety conditions. Safety conditions in control scripts help keep chemical processes within safe operating limits. They check key values such as temperature, pressure, or concentration against engineering thresholds and flag situations that may be unsafe, such as excessive reactor temperature or pressure problems in a distillation column. In this way, engineering judgment becomes consistent rules that computers can apply to support safety and reliability. Engineering scripts often use conditional logic because safety depends on several factors at once, such as temperature, cooling, agitation, pressure, or vent status. These checks help reflect the real operating context and make it clear why a situation is considered safe or needs action. They improve reliability and understanding, but they do not replace formal safety systems. Safety conditions should be clear, conservative, and understandable to engineers who did not write the script. Avoid ambiguous thresholds or hidden conversions, and handle boundary cases and sensor failures explicitly. Missing data, such as an absent pressure reading, should be flagged rather than treated as safe. Well-written safety logic supports safer decisions and keeps operations aligned with responsible engineering practice. Python code, safety conditions. Define safety boundaries with clear conditions and treat any missing measurement as unsafe rather than assuming it is acceptable. Before declaring a process safe, combine all relevant process facts so the decision reflects the full available information. The reactor state is summarized by 4 key values: a temperature of 132 degrees Celsius, unknown pressure data, a cooling flow of 48 liters per minute, and an active agitator. These values support safety monitoring, while the missing pressure reading must be handled carefully in any safety check. The safe operating limits are set as 130 degrees Celsius for temperature, 450 kilopascals for pressure, and 40 liters per minute for minimum cooling flow. A safe status label is also defined to clearly mark when these conditions are acceptable. The code starts with a cautious default decision to review the situation. This means the condition is considered uncertain and needs engineering attention before it can be treated as safe. By doing this, potential issues are flagged for further examination instead of being missed. The system first checks whether the pressure reading is missing. If no reading is available, it cannot assume the situation is safe, so it raises an alert. The alert reason is that the missing pressure value needs immediate attention. The code compares the current temperature with the maximum allowed limit. If the temperature is at or above that limit, it triggers an alert and records overheating as the reason, so the issue can be addressed immediately. The code checks whether the pressure has reached or passed the maximum safe limit. If it has, the system marks the decision as an alert because the reactor may no longer be operating safely. The code checks whether cooling is too low or the agitator has stopped. If either problem is present, it raises an alert because inadequate cooling or mixing could make the reactor unsafe. If no alert conditions are met, the reactor is considered safe. The decision is set to safe because all required measurements satisfy the safety rules, confirming normal operation. The code prints a brief reactor safety summary. It reports whether the reactor is safe or needs attention, gives the reason for that decision, and shows key operating conditions: temperature, pressure, cooling flow rate, and whether the agitator is running. Together, these values provide a quick snapshot of the reactor's current status. This script checks reactor safety using temperature, pressure, cooling flow, and agitator status. It starts with a conservative review decision, then raises an alert if pressure data is missing, temperature or pressure is too high, cooling flow is too low, or the agitator is off. If none of these problems are found, it marks the reactor as safe. The output summarizes the decision, the reason, and the current readings. Looping over conditions. For loops. A for loop repeats the same calculation for each value in a collection, making it useful for engineering comparisons across changing conditions. Instead of rewriting instructions for each case, you place the repeated work in one block and run it automatically for each item. This keeps scripts shorter, clearer, and less prone to errors. A for loop works by taking each item in a collection one at a time and using it inside the loop. In chemical engineering, this can help evaluate different conditions such as temperature, pressure, or flow rate. The loop applies the same calculation to each case, making it easier to compare results, study process behavior, and identify trends. For loops, let engineers test many conditions in a consistent, organized way. By recording and comparing results from each run, a script becomes a simple computational experiment that can reveal better operating choices, such as improved yield or safer pressures. Careful loop design is important, so the analysis answers the right question and preserves the needed results. Python code, for loops. For loops repeat engineering calculations under a set condition, helping produce results that can guide process decisions. A set of feed temperatures ranging from 300 to 380 degrees Celsius is defined for later calculations. These values will be used to compare conversion rates under different operating conditions. Set the minimum acceptable conversion rate to 0.55. This threshold is used to check whether calculated conversion values meet the process requirements. We begin by creating an empty list to store conversion results. As the program loops through temperatures, it will add each temperature and its converted value to this list for later analysis. We loop through each temperature to calculate its estimated conversion rate. This lets us check whether each temperature condition meets the required specifications. The conversion rate is estimated from the current temperature using a simple linear relationship. It starts at a base value of 0.4, then increases slightly by adding 0.0012 times the temperature in Celsius. Each temperature is paired with its converted value and stored as a tuple in the conversion results list. This keeps the original and converted temperatures organized together so they can be easily accessed or analyzed later. The program first prints a clear table heading for Celsius temperature, conversion rate, and status. This organizes the loop output so the results are easy to read and interpret. We go through each stored temperature and its matching conversion value together. This lets us evaluate each result in context and apply any further logic based on the conversion outcome. The code compares the calculated conversion with the minimum required threshold. If the conversion is at least that high, the operating condition is considered acceptable for safety or performance. This code checks whether the conversion rate meets the required minimum. If it does, the status is marked as acceptable, meaning the operating conditions are within the desired specifications. This code checks whether the conversion value falls below the required minimum. If it does, the operating condition is marked as below specification, making it easy to identify conditions that fail to meet safe operating standards. This code marks a condition as below spec when the conversion value falls under the minimum required threshold. This label makes it easier to identify temperatures that do not reach the desired conversion level. This line prints a neatly formatted summary of each condition, showing the Celsius temperature, the converted value, and a status label. The temperature appears as a whole number. The conversion uses 2 decimal places, and the status indicates whether the condition is acceptable or below specification. This makes the calculation results easy to scan and compare. After the loop finishes, the code finds the operating condition with the highest conversion. It uses the maximum function to compare results by their conversion value, then extracts the matching temperature and conversion. This identifies the process's optimal operating point. The code finds the operating point with the highest conversion from the results. It uses the maximum function to compare entries by conversion value, then reports the matching temperature and conversion. The final output is a formatted message showing the best temperature in Celsius and the conversion rounded to 2 decimal places. This script compares chemical conversion rates across several temperatures to see whether each meets a minimum requirement. It estimates conversion with a simple linear calculation, reports whether each result is acceptable or below specification, and identifies the temperature with the highest conversion. The output is a concise results summary and the best operating condition. While loops. A while loop is useful when a calculation must continue until a condition is satisfied, rather than for a fixed number of steps. In chemical engineering, this fits tasks such as checking a reactor temperature until it is safe, or adjusting a recycle stream until its composition changes very little. The loop keeps running while its condition is true and stops when the condition becomes false, making it well-suited for processes controlled by system behavior. When writing a while loop, make sure something important changes each time the loop runs. In engineering calculations, failing to update values such as volume or temperature can cause endless loops or misleading results. A reliable loop needs a starting state, a clear stopping condition, and an update that matches the physical process being modeled. When using while loops in engineering calculations, safeguards are essential to prevent unreliable or endless runs. A calculation may fail to converge or may oscillate, so engineers set iteration limits and stopping tolerances. These practices help scripts behave predictably and stay consistent with realistic process and operating limits. Python code, while loops. While loops repeat a process until a condition changes. In engineering calculations, each iteration updates the system state, and safeguards help prevent the loop from running out of control. The tank filling process starts with a target of 25 liters. The tank already contains 2 liters. Liquid is added at 3.5 liters per minute, and the timer begins at 0 minutes. The setup begins by limiting the simulation to 10 minutes so the loop cannot run forever. It updates the tank volume once per minute, starts the iteration count at 0, and begins with a status message saying the target volume has not yet been reached. This status will change depending on the loop's result. The tank filling setup begins with a target volume of 25 liters. It starts with 2 liters already in the tank, fills at 3.5 liters per minute, and tracks elapsed time from 0 minutes. Inside the loop, the system checks whether the elapsed time has reached the safety limit. If it has, it updates the status to show the process was stopped and exits the loop, preventing further operation beyond safe conditions. The program checks whether the tank's current volume has reached the target volume. If it has, the tank is considered filled to the desired level, and the status message is updated to show the target was reached safely. This confirms the loop ended successfully without triggering the safety limit. This output summarizes a while loop used to model tank filling. It reports how many iterations ran, the final elapsed time, and the final tank volume, with the time and volume shown to 1 decimal place. It also gives a status message explaining whether the target volume was reached safely or the process stopped because of the safety limit. This script uses a while loop to model filling a water tank from 2 liters toward a target of 25 liters. Each minute, the volume increases by 3.5 liters, and the loop tracks both time and progress. It reports success if the target is reached within 10 minutes, or stops if the safety time limit is exceeded. The final output summarizes the number of loop iterations, elapsed time, final volume, and whether the target was reached. Range iteration. Range iteration lets chemical engineers repeat calculations across changing conditions, such as temperature or pressure, without rewriting the analysis each time. By looping through each condition in an organized way, it makes process evaluation more efficient, reduces errors, and simplifies changes to the study. For example, reactor conversion can be estimated across multiple temperatures by evaluating one condition per loop iteration. Range iteration depends on choosing the right start, stop, and step size. Larger steps can reveal broad trends quickly, but may miss important changes, while smaller steps give more detail at a higher computational cost. Engineers often begin broadly, then narrow the range for closer analysis, especially in safety reviews where behavior at specific increments matters. This makes range iteration both a calculation method and an exercise in engineering judgment. Range iteration samples selected points rather than every possible condition. So choose ranges that match the system's physical limits, such as pump capacity or pressure ratings. Check whether endpoints are included and whether the step size is fine enough for the process being studied. Used well, range iteration acts as a structured experiment for exploring and communicating process behavior. Python code, range iteration. Range loops help evaluate planned operating conditions by running one pass for each reactor temperature. The resulting small tables make trends easier to see without repeating the same analysis. We define a Celsius temperature range to test reactor performance under different operating conditions. The temperatures run from 300 degrees up to just below 381 degrees, increasing in 20-degree steps, so the reactor can be evaluated at regular intervals. We start with an empty list to store the conversion percentages for each temperature. This makes it easy to review and analyze the results later in the script. For each temperature in the range, the rate constant is calculated as 0.0015 times the temperature above 280. This temperature-dependent rate is then used to find the conversion as 1 minus an exponential decay term over 8 time units. The resulting conversion shows how efficiently reactants become products at each temperature. The code converts each decimal conversion value into a percentage by multiplying it by 100. It then pairs that percentage with the current temperature and stores the pair in a results list for later analysis and display. The output begins with a header that identifies the results as a temperature sweep for a small plug flow reactor. It then labels the two columns as temperature in Celsius and conversion percent, giving the calculated data a clear structure for comparing temperature with conversion efficiency. The program displays each sampled operating condition by going through the temperature and conversion results. For each pair, it prints the temperature and its conversion percentage in aligned columns, with the percentage shown to 1 decimal place. This creates a clean, table-like output that makes the data easy to read and compare. We set the target conversion at 60%, which is the minimum reactor performance we want to reach. A tracking flag starts as false and will change to true if any temperature in the tested range meets or exceeds that target. This lets us determine whether the analysis found an acceptable operating temperature. The process checks each temperature and conversion value until the conversion reaches the 60% target. When the target is first met, it reports the corresponding temperature, marks the target as achieved, and stops searching. This finds the earliest qualifying temperature while avoiding unnecessary checks. The code checks whether the target conversion was reached anywhere in the tested temperature range. It tracks this with a Boolean flag, and if the flag remains false, it means no tested temperature met or exceeded the target. The code then reports that the target was not achieved, giving feedback on the temperature sweep's effectiveness. The script models a temperature sweep for a plug flow reactor to see how conversion changes from 300 to 380 degrees Celsius. At each temperature, it calculates the reaction rate constant, estimates the conversion percentage, and reports the results in a simple temperature versus conversion summary. It then checks whether the process reaches at least 60% conversion and identifies the first temperature that meets the target, or reports that none do. This helps evaluate how temperature affects reactor performance and supports choosing suitable operating conditions. Debugging basics. Identify logic errors. A logic error occurs when a script runs without crashing, but makes the wrong decision. Pausing. Unlike syntax errors, these problems can be hard to notice because the output may look reasonable. In engineering, this can be dangerous, such as when a script incorrectly labels a borderline unsafe reactor temperature as safe. To find logic errors, compare what the script does with the real engineering rules it is supposed to follow. To find logic errors, restate each condition in plain language and check that it matches the situation being modeled. Be precise about boundaries, such as whether a limit is included or only values above it should trigger action. Also check both ends of ranges, since reversed comparisons or missing limits can cause serious mistakes. In engineering scripts, these errors may lead to wrong equipment choices or missed safety alerts, even when the program runs without crashing. To find logic errors, test your script with inputs where you already know the correct result, including normal values, extreme cases, and boundary values. In a separation process, this means checking values within, outside, and at the limits of the operating range. If the output is wrong, focus on the decision logic and trace how each value moves through the program's conditions and branches. Python code. Identify logic errors. Logic errors can remain hidden even when a script appears to run correctly. Testing boundary cases helps uncover mistakes in engineering decisions, and plain language rules make it easier to correct conditions accurately. We create a Celsius temperature test list with values just below, at, just above, and well above 80 degrees. This checks whether the safety rule behaves correctly around the critical 80-degree boundary. The code states the reactor's safety rule. It is safe when the temperature is 80 degrees Celsius or lower. If the temperature rises above that limit, caution is needed. This message sets up the safety condition used by the logic that follows. The buggy label function classifies a Celsius temperature as safe or caution, using 80 degrees as the threshold. It currently returns safe when the temperature is below 80 and caution otherwise. This uses the wrong comparison for the intended boundary, so the safety classification is reversed. The corrected label function classifies a Celsius temperature using a simple safety rule. Temperatures up to and including 80 degrees are labeled safe, while anything above 80 degrees is labeled caution. This matches the intended rule for identifying whether the temperature is within the safe range. The output first labels the columns for temperature, the buggy classifier, and the corrected classifier. It then checks each test temperature with both classifiers, comparing whether each one marks it as safe or caution. This side-by-side comparison makes it easy to spot where the flawed logic gives a different result from the corrected version. The code prints one formatted line for each temperature test value. It shows the Celsius temperature to one decimal place, then compares the results from the buggy and corrected classifiers. The aligned safe or caution labels make differences between the two versions easy to spot. The message identifies a logic error at the exact boundary of 80 degrees Celsius. It shows that the earlier safety check is wrong because 80 degrees should still be treated as safe, but the buggy logic excludes it. Highlighting this boundary case makes the mistake clear. This example shows why boundary conditions must be handled carefully in logic. A reactor safety rule says temperatures at or below 80 degrees Celsius are safe, but the flawed version marks exactly 80 degrees as caution. Comparing it with the corrected version reveals the mistake at the boundary, showing how boundary testing can uncover logic errors in code. Loop logic errors. Loop logic errors occur when a repeated process runs the wrong number of times or updates values in the wrong order. In engineering scripts, they can be hard to notice because the program may still run but produce unreliable results. These mistakes often come from incorrect starting points, stopping conditions, or loop progression. When debugging, check that the loop covers exactly the intended conditions, not just that it finishes without crashing. Loop errors usually happen when the condition does not match how values change during each pass. If values are not updated correctly, a loop may run forever or skip important steps. Mistakes can also come from placing calculations inside the loop when they belong outside, or the reverse, which can produce wrong results. To debug, check what changes each pass, what should stay constant, and what must be reviewed after the loop finishes. To debug loop logic, examine how the loop behaves on individual repetitions, especially the first, middle, and last passes. In chemical engineering scripts, this means confirming that recalculations, safety checks, and optimization conditions are evaluated correctly each time. Pay close attention to boundary cases at the start and end of a range, and treat every loop as a controlled sequence with clear entry, update, and exit points. Python code, loop logic errors. When debugging, pay close attention to loop boundaries to avoid missing or repeating cases. In chemical problems, make sure every required case is covered exactly. If calculations repeat, trace them clearly so errors are easier to find. This line means the script can run in a standard Python environment without installing extra software or external packages. It helps ensure the code is easy to use and share, even with people who do not have additional libraries set up. A set of reactor operating temperatures is defined in Celsius: 300, 320, 340, and 360 degrees. These values will be used to calculate the conversion for each operating condition. Begin by creating a list to store each temperature with its converted value. As each conversion is calculated, add it to the list so the results stay organized for later comparison or analysis. For each Celsius temperature, a conversion value is calculated by adjusting a base value of 0.45 according to how far the temperature is from 300. The adjustment adds 0.001 times that difference. Each temperature is then paired with its calculated conversion value for later analysis. This code stores each Celsius temperature together with its converted value as a pair in the list of correct results. Keeping the original and converted values together makes it easier to check the calculations later and confirm that every temperature was handled accurately. A results list is created to store temperature conversions from a loop that contains an off-by-1 error. Because of the loop mistake, the list will miss some intended data. This makes it useful for comparing incorrect loop behavior with the correct version later. The loop is intended to process each temperature in the list, but its range stops before the final index. As a result, the last temperature is skipped. This causes the data processing to be incomplete. The code computes a conversion value for each Celsius temperature. It starts from 0.45, then adds a small adjustment based on how far the temperature is from 300. The loop stores each temperature with its converted value in a results list so the outputs can be checked later. Because the loop range has an off by 1 error, it skips the final temperature. Comparing these stored pairs with the correct results helps reveal the discrepancy caused by the faulty loop logic. The code displays the planned reactor temperatures so they can be checked before further processing. This helps confirm that later calculations and comparisons use the correct temperature data. We create a concise list of the temperatures that the buggy loop actually processed. This is done by going through each buggy result and keeping only its first value, the temperature. The resulting list can then be compared with the intended temperatures to see what the loop handled. We extract the temperature values from the list of correct results. Each result is a tuple, and the temperature is stored as its first item. A list comprehension collects those first items into a new list containing only the temperatures that were processed correctly. The code compares the temperatures handled by a buggy loop with those handled by the correct loop. By showing both results, it makes any differences visible and helps reveal logic errors in the loop's behavior. The code finds missing operating conditions by comparing the set of expected temperatures with the set handled by the buggy loop. Any temperatures present in the correct set but absent from the buggy one are identified as missed cases, then sorted for clear review. This helps verify that the loop covers all intended conditions. The code reports temperatures that a faulty loop failed to process. This makes it easier to spot gaps in the loop's coverage and confirm that all intended temperatures are included in the calculations. The code prints the number of stored conversion results to confirm that each temperature was processed. If the count matches the intended inputs, it shows that the loop completed correctly and saved every result. This script shows a common off-by-1 loop error while processing reactor temperatures. The correct loop handles every temperature and stores each conversion result, while the buggy loop stops too early and misses the final temperature. By comparing the intended, buggy, and correct outputs, the example highlights why loop boundaries must be checked carefully to avoid leaving out important data. Print debugging. Print debugging helps reveal control flow problems by showing key messages while a script runs. In engineering scripts with conditional rules, unexpected results may come from the program taking the wrong logic path rather than from incorrect calculations. Adding brief messages near important decisions makes the script's reasoning visible and helps confirm that it follows the intended path. Print debugging works best when you choose carefully what to display and where to display it. Add prints at key control points, such as before decisions or around loops, to show important values and whether stopping conditions are being reached. In simulations or heat exchanger scripts, this helps reveal problems like unchanged values, wrong thresholds, or unexpected design choices without overwhelming the output. Print debugging works best when used deliberately and removed after the problem is fixed. Clear messages should explain where they come from and what each value means, not just display raw numbers. This helps test assumptions and reduces mistakes, especially in engineering scripts that may be reused or shared. Although advanced debugging tools offer more control, print statements are a quick, transparent way to find where a program's logic starts to differ from the intended reasoning. Python code, print debugging. Print debugging helps show which control flow paths a program takes, especially when chemical rules depend on conditional branches. Diagnostic messages should be brief and focused, so they clearly reveal the key decisions being made. We define a list of reactor temperatures in degrees Celsius, 72, 81, 89, and 96. Storing them together makes it easy to check each operating condition against a safety limit. The reactor temperature safety limit is set at 90 degrees Celsius. Actual temperature readings are compared with this threshold to determine whether operation remains safe or a warning is needed. Begin by setting the safe count to 0 so the program can track how many reactor temperature readings fall within the safety limit. Starting at 0 ensures the count is reset before checking the readings. The debugging output begins with a clear introductory message about reactor temperature decisions. This sets the context so readers understand that the following information explains the control flow related to reactor temperature handling. A loop processes each reactor temperature in the list one at a time. The enumerate function provides both the temperature and its position, with counting starting at 1 to make reporting clearer. The code displays the current run number, temperature in Celsius, and safety limit before making a decision. This makes debugging easier by showing the key values being checked and how the program's control flow is progressing. The code checks whether the current temperature stays within the safety limit. If the temperature is at or below that limit, the system is considered to be operating safely. This decision helps confirm that the reactor remains within safe operating parameters. This line prints a message when the temperature is in the safe range. It confirms that the program entered the safe temperature branch, which helps track control flow during debugging. This line increases the safe count by 1 whenever a temperature is within the safety limit. It helps track how many operating points are safe for the reactor. When the temperature rises above the safety limit, the program enters the safety warning branch. This shows the reactor is beyond the safe threshold, and the printed message confirms that the potentially unsafe condition has been detected. This message shows that the program has entered the safety warning branch. It alerts the user that the temperature is above the safety limit, indicating the reactor may be operating outside safe conditions. The code reports how many reactor temperature readings were within the safety limit. It does this by using a counter that increases each time a safe temperature is found, giving a simple diagnostic summary of safe operating conditions during debugging. This script checks reactor temperatures against a safety limit of 90 degrees Celsius. It reports each temperature, marks safe readings, warns when the limit is exceeded, and counts how many readings are within range. This makes the control flow easy to follow and supports clear debugging. In this lecture, you learned to write conditional statements that encode chemical engineering decision rules, use loops to repeat calculations across ranges of operating conditions, and debug simple control flow errors in engineering scripts. In the next module, Module 2, we will go over data structures. Thank you for your attention. See you all in the next lecture.